So here we have the differential equation x plus y plus 1 whole squared times dy equals to dx, and this is an initial value problem with some boundary conditions provided here. So we need to find a solution to this given differential equation by using the method of variable separation. So let us begin by rewriting the differential equation. So we will divide both sides with dy. So that means this gives us dx over dy equals to x plus y plus 1 whole square. Now clearly the term on the right hand side is a function of x, y. So that means this cannot be, we cannot separate it by using the method of variable separation. So here we have to suppose that let x plus y plus 1 equals to some variable v, and we differentiate both sides with respect to y. So we have dx over dy plus differentiation of y with respect to y will be 1 plus 1 is a constant, so that's 0 equals to dv over dy. So if we isolate dx over dy, so that will be dv over dy minus 1. Now we take this value and substitute it back to our original differential equation. So we will now get dv over dy minus 1, and that's equals to, so we have x plus y plus 1, which we have assumed the value v, so this will be v squared. So we have dv over dy equals to 1 plus v squared. Now we can separate the differentials and rewrite this as dy equals to dv over 1 plus v squared. Now you can clearly see that this is in the separable form, so that means we can integrate both sides. Integration of dy, that's pretty straightforward, which is y, and integration of dv over 1 plus v squared. So here we will use the formula from the table of integrals. So if we have du divided by a squared plus u squared, so that simply equals to 1 over a times tangent inverse or the arc tangent of u over a plus the constant of integration c. So in our integral, we have the value of a is equals to 1, and our variable u is simply v. So that means we have 1 over a, so that's 1 over 1 times the arc tangent of v over 1 plus the constant of integration c. And we have to replace the value of v with x plus y plus 1. So we should get y equals to tangent inverse of x plus y plus 1 plus the constant c. So now our task will be to determine the value of this constant c, and we can use the initial conditions here. Since we are provided y of minus 1 equals to 0, so this means that when x approaches the value negative 1, then y is going to approach the value 0. So let's substitute this value into our general solution. So we have y, so y will be 0, that's equals to tangent inverse of x. So x value is negative 1 plus y, which is 0, plus 1 plus the constant of integration c. So here we have negative 1 and 1 cancelling each other. So that's simply tangent inverse of 0 plus c, and we know the tangent inverse of 0 is 0. So our constant value c comes out to be 0, and let's substitute this value here, and that gives us the value y equals to tangent inverse of x plus y plus 1 plus 0. And if we take the tangent function on both sides and rearrange the equation, we should get x plus y plus 1 equals to tangent of y, and this is the required solution to our given differential equation.